Hi guys, welcome back. Today we're covering 4.5, the chain rule in multivariable. I'm going to try to quickly remind you about the chain rule in one variable with a picture that I think should be really helpful. So this counts as something we're recalling, something we should already know. I want to imagine a little word problem just to really give you something to visualize. So let's say that this is X and this is Y, and that we have this little game going where you are moving along the X axis. So let's say you are moving this way, and we're going to visualize maybe your friend moving this way at the same speed. So you are here, your friend is here, and between the two of you, there's a square of space that has some area to it. So let's give um, that area an amount. If it's a function of x, the area would be x squared. And then let's say that you are moving, so you have a position on the x-axis, and that position is given by a function of t, and I'm going to go with a speed s, so this is some constant, times t. Your friend is also moving at s times t on the y-axis. If s is 1, maybe you're moving at 1 foot per second. If s is 3 feet per second. If s is 0, you're not moving at all. Then the area at a given time as a function of t is equal to this function f. I want to change something, sorry. Instead of p here, let's call this x of t. X of t. Which is st squared. And then by the chain rule, if you wanted to know dA dt, you would use the formula f prime times, f prime at x of t times x prime of t. Or this is the same as differentiating the outside, 2 times s of t times the derivative of the inside, which is s, so 2 s squared t. Whoops. And I just want to pay a little bit of attention before we go into the lesson for today on these two pieces, f prime and x prime. If we go back over here and look at this rectangle or square, let me say, uh, wherever you are, let's say you're right here and you move in this direction, the area gets bigger. If you were down here and you moved the same amount, the area would still get bigger, but it would get bigger by less. That red amount that the area is increasing by, that's the f prime, which is 2x. But there's a second part going on here, which is the following. If you started at this same point, but you moved twice as fast, in the same amount of time, roughly speaking, you would actually gain twice as much area. And that's true down here as well. If you move twice as fast, then in the same amount of time, roughly speaking, you're gaining twice as much area. And what you're seeing in blue there, that's your speed. That's like your x prime of t. So there's these two things together that determine how much your function changes. One of them is how much the quantity changes for some amount of movement in x. And the other part is how much movement in x there actually is. For instance, if you didn't move at all, the area wouldn't change, no matter how big this is. So try to keep that in mind when we do the chain rule. There's these two elements involved. How much the function would change, we're calling that's how I'm thinking of f prime, if we moved, and then how much we're actually moving. Let me actually write those words in because that's pretty useful. How much change in f if we move. And then this guy here is like as how much we actually move, how much we actually move. And by much here, I'm referring, these are rates of change, so these are derivatives, of course. Okay, so that's all a recollection. That's just to get the gears turning so you're ready to learn. And now let's jump into what the chain rule actually looks like for in multivariable. There's going to be more than one form of this, but let's start off by saying we have a function of two variables now, uh, x and y. And instead of having x as a function of t, we have now x and y both. I'll write it this way. Let me write it this way. X and y are both functions of t. So collectively now we can ask this question. I'm going to use partial notation because we're oh no, actually no, I'm not. Sorry, I have to say something about this. But um, if you think of z now as a function of t, it would look like this. You would plug in some t value into x and some t value into y. And now z is a function of t, and there is a derivative, how much z changes with respect to t. So I'm just going to write this formula first, and I'm going to try to describe what it's telling us and then do some examples. So if you understand this little snippet that I try to throw in here, there's how much the function changes if we move, and then how much we actually move. So there's two parts to how much z changes when we vary t. There's an amount z changes in the x direction times how much we move in the x direction. Plus there's an amount that f changes if we move in the y direction. And then there's how much we actually move in the y direction. Now, I don't want to write what I'm going to say next, so I'll just say it. We use the partial notation on f because f is a function of two variables, x and y. We use the standard d lettering for dx dt and dy dt because x and y are both single variable functions. These are not partial derivatives. We're back in single variable calculus for these two guys. So let's just write this. This is it right here. This is the chain rule. I'm going to say version 1. It's right here. A sketch of what's going on there to really hit the idea home before we do any examples. Let's imagine, let's see what's a good graph to do here. Let's try to do like an upward facing paraboloid. And let's imagine that in X and Y, we're maybe at a point like right there. Zoom in a little bit. From this point, there's two directions we can move, really. Two independent directions. There's movement back and forth in the X direction. There's also movement back and forth in the Y direction. So if we vary in the X direction, this corresponds to some dx dt. So we go forward in time and maybe we move to the right, maybe we don't. And if we go forward in time, we also have possibly some dy dt. We may move up or down. We might move upwards some, we might move downwards some, we might not move at all. This depends on what y is, what function of ty is, and what function of tx is. Let's try to throw in one more color. I think I should have done this differently. So let's say the starting point on the graph is right there. You can see there's a tangent line in the x direction telling you how much you go up or down when you move in the x direction. And there's a second line, let's do it with a different color. A tangent line in the y direction. So the slope of the orange line would be, let's say, partial z or partial f, you could say, partial y. And then the slope for the green line is partial z partial x. So if we move to the right, let's say, there is a change, dx dt. You can think of this like how much we change in the x direction, delta x. And then there's this slope in the x direction. And just imagine that slope is 0 first. Then whether you go to the right or not, the function value won't change up to first order. But in general, that slope is not 0. And so whatever it is, it's going to tell you how much you go up or down. You can think about that as how much z changes when you change in the x direction. And then just throw in the other two guys. It's the same exact thinking for the other one direction. Partial z, partial y, dy dt. These guys you can think of as how much z changes when you change in the y direction. And then there's a question of how much you actually change in the y direction. Let's just jump in with some examples and then maybe it'll become more clear. Oops. Here's my first example. I'm not sure I'll do two. Maybe we'll do two. Okay, the first example is z equals a function of two variables, x and y, and that function is 4x squared plus 3y squared. They also give us functions x and y. X is a function of t, it's sine of t. And y is cosine of t. And they ask us to solve for dz dt. I'm merely going to apply the above formulas with no real insight, and then I'm going to see if I can say something about it afterwards. So I need to do two things here to find this derivative. Or maybe four things if you want to think about it this way. First, I need to differentiate f with respect to x. That's just 8x, the 3y squared vanishes. And then I need to multiply by dx dt. This is cosine of t. I also need to differentiate f with respect to y and multiply by dy dt. And then if you want to leave it in a nice closed expression, thinking of z as a function of t, then you can go and take x and y, replace them with their equivalent expressions in t, and you'll get, let's do it all out, 8 sine t cosine t minus 6 cosine t sine t, or just 2 sine t cosine t. I'm going to show you one thing real quick. What if we had started and just said z is equal to 4 sine squared plus 3 cosine squared? That has to be true because you just take x and y and plug them in. Now, there is no chain rule. There's no multivariable. This is z as a function of t, single variable calculus. And you could, in this context, just differentiate directly. What do we get? 8. Well, the derivative of sine squared is, here I'm using the chain rule, sine cosine. And then the same deal with the cosine squared, you'll get a plus 6. The derivative of the cosine squared, that 2 comes down. You pick up a cosine and also a negative sine, and you can see you get the same answer. 2 sine t cosine t. This is always the case. If you can reduce your thing to something you already know, where you know how to do something, you better get the same answer, right? Math is an internally consistent set of rules. You shouldn't get something different by using a more advanced technique. Yeah, so I'm afraid to try to draw something that's too complicated. I think I'm going to try. I'm going to try to give you a quick drawing here. So 4x squared plus 3y squared is an upward facing ellipsoid. So its level sets look like this. It goes up. It goes up faster in the x direction because of that 4. It goes up more slowly in the y direction because of that 3. And so the level sets of this function are elliptical. I'm kind of exaggerating the elliptical behavior to hit the point home. It's got elliptical level sets. We're not seeing that whole function. We're only seeing this here, which hopefully everybody recognizes as a parametric curve. Maybe just pause a moment, try to remember how parametric curves work, and if you can remember what this parametric curve looks like, sine t, cosine t. This is a circle, and if this is x and this is y, it starts off at y equals 1 and x equals 0 when t equals 0. And then as we increase t, this green curve just goes around and around and around and around. As we increase t, we just see these sine and cosine values trace out this circle. Now here's the lead that I was kind of afraid to draw. I'm still kind of afraid to draw it, but let's go for it. One more color. The red function, right, of two variables takes values over this green curve. If you take any point on the green curve, you'll get a point on the red function, right? And it's smallest over here. It's largest on the x-axis on both sides of the x-axis. It's smallest on both sides of the y-axis. And here's what it does. Let's go for it. It goes up and down as we go around the circle. Right, so as you go around that circle, the blue curve goes down, and then it goes up again, and down, and then up again. And it just kind of keeps on doing this as you go around and around and around. And that right there, that is what we're calling z of t. And when you find dz dt, you're asking, does this curve, whatever t value you're at, is the curve going down? Is the curve going up? Is it flat? Does it have a zero first derivative? It's not going up or down? Is it flat here, flat there? All of these places on this curve, there's either some upward motion, some downward motion, or some flat motion. And which one you're seeing depends on what t value you're at. And dz dt is exactly what we're calculating when we do that. So just try to keep that in mind. Whenever you see these problems, x and y collectively are being given t, values based on t. That generates a parametric curve. And the function f that you're given, restricted to that parametric curve, becomes a new curve. And that new curve, that's what we're differentiating. Without any more pictures, just one more quick calculation example for completeness sake. Let's go through B of that same example. This is what they give us. So z equals f of x, y equals root x squared minus y squared root x squared minus y squared. X is e to the 2t. Excuse me. Y is e to the negative t. So let's just really quickly do this. dz dt is, first I differentiate f with respect to x. I'm going to kind of do this quickly now. X over the square root of x squared minus y squared. This is the chain rule. The 1/2 comes down. You differentiate the inside. You get 2x. The 2's cancel. And so that right there is f sub x, the derivative with respect to x. I need to multiply this by dx dt. That's just 2e to the 2t. I also need df dy. There's a negative sign that gets picked up from the inside of the chain rule there. Negative y over root x squared minus y squared. And then this gets multiplied by the derivative dy dt, negative e to the negative t. And again, I'm going to go ahead and put everything in terms of t again, just for the sake of neatness. So I've got 2 e to the 2. Let's do 4 to, so e to the 2t, that's x times e to the 2t. Let's do 4t. One, go back. E to the 4t over denominator. I've got e to the 4t minus e to the 2t. Two negative signs cancel. I get plus. Y is y is e to the negative t, so this is e to the negative 2t, and this should be negative 2 as well here. Over root, same thing, e to the 4t minus e to the negative 2t. And then we can simplify a bit, 2e to the 4t plus e to the negative 2t over root e to the 4t minus e to the negative 2t. And I think you could probably simplify this more. I'm not so sure that I want to. I don't think it's going to get all that much better. Yeah, I'm thinking about multiplying the top and the bottom by e to the 2t, which is the same as multiplying by 1. And then these guys will turn into 1 and you'll get 6 t's. I don't really care if you do that or not. You can if you want to, but we'll call that a complete example right there. Okay, so that's 2 examples of the chain rule where x and y are functions of t. That's kind of the first chunk of this section. Now I'm just going to write this out, chain rule version 2. There's no new insights here. There's just more variables. So now the context, so let me just remind you what the first one was. First one was right here. Z is a function of x and x and y are each functions of t. Now I want to do z is a function of x and y, but x and y are each functions of two variables. Here they usually use the letters u and v. So we are not reducing the number of input variables, we're just changing them. And so now collectively, we can think of z as a new function, a function of u and v. If we write it this way, f of x of u and v, y of u and v, and now both are all three, f and x and y, are all multivariable functions. So every bit of differentiation will use the partial derivative notation. And now, take a moment and just think about it. Now there's two derivatives we could theoretically be asked to find. There's whatever the partial derivative with respect to u is of z. I'm going to put the input variables in there. No, I won't. We don't need them for right now. We'll put them in when the time comes. And there's also the partial derivative of z with respect to v. If you want the derivative of z with respect to u, here we go. Differentiate f with respect to x and ask how much does x change when we vary u. Also differentiate f with respect to y. And now you must ask how much does y change when we vary u? And there's an entirely separate formula because we could ask how much does f change when we vary x and how much does x change when we vary v? And over here, same deal. How much does f change when we vary y and how much does y change when we vary v? Let me do the same order before. So first I did a picture. No, first I did an example, then a picture. Let's try to do an example where we just calculate all of this, and then I'll try to give a little bit of an image for what's going on here. Where's my example? Yeah. So here's what they give us. Z is equal to, I'm going to skip the F part, 3x squared minus 2xy plus y squared. X is 3u plus 2, 3u plus 2v. And y is 4u minus v, 4u minus v. So here's just the mathematics, no fluff. Partial z, partial u is differentiate z with respect to x, 6x minus 2y, and then differentiate x with respect to u, that's just 3, right? The derivative of that with respect to u is just 3. Differentiate z with respect to y, and y with respect to u, that's just 4. Here now, if we want to keep things in terms of u and v, then we want 3 times 6 times 3u plus 2v minus 2, 4u minus v, and then plus 4 times minus 2 times 3u plus 2v plus 2 times 4u minus v. And then I'm trying to decide what to suggest here. So let me say something here. So let's say first that we didn't do that. I'm going to make a point here. So I would have 18x minus, sorry, 18x minus 8x is 10x, and minus 6y plus 8y is plus 2y. That's one form of an answer. It's written in terms of x and y. And now down here, it's much worse. So there's going to be a lot of simplification here. As long as you don't do any arithmetic wrong, you have to get this same answer. So we know that you have to get 30u plus 20v plus 8u minus 2v, 38u plus 18v. So there are times when you might not want to do this arithmetic to get to this answer. And it's also perfectly okay to leave your answer in terms of x and y. So this is good. This is good. And also, by the way, this is not the end of the world. With these earlier guys up here, you can leave it mixed. So if you left it like this, there's x and y and t. It's a little bit clumsier, but it's also fine. What you really want to ask yourself is, did the problem ask me a follow-up where I need to evaluate this? Because if it follows you up and says, evaluate it with u equals 1 and v equals 1, then you need this form. Unless you want to take u and v, plug them back into x, and then plug those guys in over here. So if there's a follow-up question, try to be smart about picking the form that works for you. But none of them are wrong. You're not going to be wrong if you put this one instead of this one. A quick drawing to differentiate between this context and the previous one where there was only the variable t. So here's the deal. Here's x, here's y, here's z. I don't know if I can draw this one. Let's see here. 3x squared minus 2xy plus, oh, we can, right? This is the same as, we can't. Right, negative sign. Yeah, it's not so simple to do this one. Let's see here. Yeah, I'm not going to attempt to try to draw that graph right there, but let me just say what's going on. Rather than having x and y parametric curves, we have x equals 3u plus 2v. And it's just 4u minus v. What do these guys give you? Let's do a quick starting point. Let's imagine that v is 1 and u is also 1. So we might have a starting point like 3 plus 2 is 5 in the x direction, so maybe like right here. And 4 minus 1 is 3 in the y direction, so maybe right here. So this point right here might correspond to u equals 1 and v equals 1. And now leave v alone, leave v as 1, and vary just the u direction. If you change u, x moves at a rate of 3 and y moves at a rate of 4. So this is over 3, up 4. You move on a line like this. This line that I just drew, that corresponds to, I'm going to put a little in quotes there, delta u, changing u. Now, if instead you fixed u and you only varied v, X would go up at a rate of 2 and Y would go down at a rate of 1. So this is over 2, down 1, over 2, down 1, over 2, down 1. And this corresponds to a line in this direction. That line there you can think of as changing V. What this does is this actually puts grid lines on the plane that are not the XY grid lines. It's a new set of grid lines, UV grid lines. They're in some other wonky direction. Hope this is clear. One more try. Come on, Mike. It's terrible, 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 terrible. So now just zoom out. Let's pretend we don't know the exact function, but I just draw another one that's easy enough to draw in a different color. You've got some, whoops, some function here, and it has partial derivatives, right? In the X direction, there's a partial derivative, and in the Y direction, there's a partial derivative. When you do this change here, this is often referred to as a change of variables. You are re-parameterizing your whole plane with respect to a new set of coordinates. And then when you find this partial Z, partial U, partial Z, partial V, those are just your standard partial derivatives, but with respect to that new coordinate system instead of the old one. You're changing out one set of coordinates, X and Y, for a new set of coordinates, U and V, and you are free to differentiate in X and Y coordinates or in U and V coordinates. That's what you're seeing happen here. One more quick example, no bluff. Hope I have one more. Or this second version of the chain rule. Oh boy, this is a long one. That might not be that bad. Well, we're gonna find out. Okay, so Z is 2x minus y over x plus 3y. U is, oh, not U, sorry. X is e to the 2u, e to the 2u, cosine 3v, cosine 3v. Then y is e to the 2 sine 3v, e to the 2u sine 3. Okay, I just said no fluff. I want to say real quick because I can't help it. If you fix u, you are fixing a radius here. And sine and cosine move in a circle. So these lines here, that right there is moving in a circle. That's changing in the v direction. Here's another circle, changing in the v direction. Whoops. Here's another circle and another circle. All of those circles represent changing in the v direction. And now if you fix v, fix this and vary x and y, you're changing the radius. So you're moving along these red lines here. And so all of these red lines here would correspond to changing u, which means the new set of coordinates that we've got right here are a form of polar coordinates, right? Circles and radial lines. So this is a new coordinate system. We're trading x and y away for this coordinate system. And this one is a form of polar coordinates, although there's an exponential speed here. So this moves away from the origin very fast. If you're, well, for large u values, it moves very fast. Anyways, you don't really need to know that, but more visualization can only make you better. Let's go ahead and do the calculations. I want to find partial z partial u. We'll do this one first. I need partial z partial x. The quickest way to do this is just going to be the quotient rule. So I want f prime g minus g prime f, that's just 1 times 2x minus y over g squared. I just differentiated that function with respect to x. And then I need dx du because I'm differentiating with respect to u. This is just 2e to the 2u cosine of 3v. I also need partial z partial y. So I want f prime g minus g prime f over g squared times partial y partial u, which is 2 2e to the 2u sine 3 3 b. I'm just going to leave this like this because no matter what, it's going to be nasty, right? So you can simplify the x and y stuff and leave it in x and y, and then leave the u and v like this. This looks complicated enough that there's no form that you're going to be very, very happy with. So save yourself the trouble. And then one more time, we can do this really quickly because the first part's the same. 2x plus 6y minus 2x plus y over x plus 3y squared. I just distributed on the top up there. But now I want, instead of dx du, I want dx dv. So this is negative 3e to the 2u sine v. And then over here, plus I've got negative x minus 3y minus 6x plus 3y all over x plus 3y squared. And then instead of partial y partial u, I want partial y partial v. 3e, the 2u cosine of, oh, I just made a mistake, 3v. This should be a 3 over here. 3, oops. 3v. And then there you go. That's the other one. Okay, that's the chain rule version 2. There's one more chunk of material in this section. I'll do it quickly. It's kind of entirely a recall, really, but a recall first. Implicit differentiation for one variable. Implicit differentiation. If you have a function f of x and y set equal to 0, and you want to know what dy dx is, there's a formula you might remember, which is negative. Do they teach this? I think they teach this, but they don't tell you that. Well, okay, I'm going to do a quick example in a second. Negative partial f partial x over partial f partial y. So the implicit differentiation you would have seen might be something like this. If x squared plus y squared minus 1 equals 0, this implicitly defines y as a function of x, at least in some places, and you would have been told to differentiate across. So you would get 2x plus 2y dy dx equals 0. And then if you solve for dy dx, you end up with negative 2x over 2y, which is just negative x over y. But this is exactly the same thing as recognizing that this is a function set equal to 0, right? That's some function of two variables. And if you differentiate, now I can use the rules that we just saw. You get this. I'm differentiating with respect to x here. This is just 1. And so this right here is that 2x times 1. That's just the 1 right there. And then the 2y is this guy, and then the dy dx. And then if you solve for dy dx here, you just recover the formula that I wrote. So negative partial, losing it, partial f, sorry. Negative partial f partial x over partial f partial y. So you've been shown this before, but in a different, written differently, because you probably have only seen it this way. But we want to extend that same thing, so I'll just write this out for a function of three variables, f of x, y, and z set equal to 0. You can solve for partial z partial x and partial z partial y implicitly using the exact same idea. If you want to know the derivative in the x direction, then you'll just only differentiate in that direction and the z direction. And then similarly, if you want to know the slope in the y direction of the function z, you just differentiate in the y direction. But this is implicit differentiation for more variables, but it is, strictly speaking, it's a repeat of things we've seen before. I'll just do one quick example where we do that stuff, and we'll call it quits on this section. Yeah, I just want to do this example. It's x squared e to the y minus yz e to the x equals 0. So that's a function of three variables set equal to 0. So if we want to, we can find partial z partial x by just taking, I'll differentiate the whole expression up there with respect to x with a negative sign on it. 2x e to the y, 2x e to the y minus e to the x derivative, that is just e to the x, y z e to the x over the derivative of this whole expression with respect to z, which is just minus y e to the x. That simplifies, but I'm going to omit that for the moment. And if I want this one, differentiate the top with respect to y with a negative sign on it. Minus z e to the x over the same thing. So those are the answers, modulo simplifying them. Also, keep in mind if you panic or you feel like you don't get where that all just came from, you are still free to do this the way that you already know how from Calculus 1. So if you look up there and I just differentiate that whole expression with respect to x, what will I get? 2x, there is a small issue here. Well, 2x e to the y minus yz e to the x. But we also, yeah, so this is not really the way I'm supposed to be teaching this, but I'll just tell you real quick. So if you differentiate that whole expression with respect to x, there's one small issue. Y is a constant, so when the d by dx hits y, nothing happens. That's treated as a constant. But in this context, z is not a constant. We are assuming that z has a non-zero derivative with respect to x, so we need to differentiate that as well. So when that d by dx comes in here, I get a 2x e to the y right? This is just a constant right here. But then at the second part over here, I've got to use the product rule. So there's one term, which is just yz e to the x when I differentiate the e to the x. But there's also the term that arises from differentiating z. And now you can solve for dz dx here. dz dx equals, this whole thing here goes to the left, negative 2x e to the y minus, so plus yz e to the x over this stuff, minus y e to the x. And you can see that right there is the same as this right here. I won't repeat it for the second one. It's the same thing. I just want to encourage you to see that if you're comfortable applying this new formula here that I'm providing you, this or really this version here, that's fine. If not, and you understand this version on the right, this is just as good. You just differentiate across, and then whatever you care about, like in this case, we cared about dz dx, just solve for that, and you'll get the same answer. So that option is also available to you. Okay, I'll state here some things that I want you guys to keep in mind. I'll also put these in an announcement on Canvas, but so this is Monday. Homework is due today. There's also a quiz today. The deadline on both of those is 8 p.m. And as per the syllabus and previous emails and announcements, I urge you to keep in mind that these deadlines are strict. So it is imperative, if you want credit for those assignments, that you pass them in prior to the 8 p.m. deadline. Also keep in mind, I have office hours tomorrow, Tuesday, and Thursday, both at noon. And if you have any questions, to please come and see me. You can also email me questions as well. Thanks, guys.